Hey class, this is Adam Ward, and I wanted to walk you through the derivation of the energy equation. This is done in your textbook, but I wanted to step through how we actually derive this. And so, if we think about ways energy could change in the system, there are basically two ways. We can either get energy in and out in the form of heat, or we can get energy in and out by either doing work to the system or having the system do work on something else around it. So written as a rate, that's the time rate of change of energy, equals the work transfer, that's the W, and of course that dot over it means it's a rate, plus the heat transfer, and so that's a Q with a dot over it. Throughout this derivation, that Q dot will refer to heat transfer, and I understand that's doubling up on Q's where we normally use it to represent discharge, but by the end we'll be rid of that terminology, so stick with me. Within a fluid itself, we can have three forms of energy. And so in that lowercase e there, I'm representing internal energies as the U with the little hat over top of it, kinetic energy or energy of motion with the V squared over 2, and potential energy represented as gravity times energy of, or times position z. And with respect to work, we'll consider functionally two kinds of work in this class. The first is what we call shaft work, and so that's work being done on the fluid by a pump, or work that the fluid is doing on something else via a turbine. Both of those occur by typically having a shaft get rotated, and so we call that shaft work. And you can see we represent that as either mass rate times gravity multiplied by the quantity of the head of a pump, HP, minus the head of a turbine, HT. You can also write that as Q times gamma, and that is the flow rate Q, if you don't want to use the mass rate notation. With respect to pressure work, you can sort of envision a piston where when you push that piston down a distance of ds, the work that you've done is the distance times area, so the volume you've changed, multiplied by the pressure change. And if we make that time variable, we could get that the pressure work rate is PAV, and rather than doing this for our cylinder, if we want to integrate that over the control surface, you get the pressure work rate is the integral over the control surface of P V dot N, so that's velocity normal to the surface, dA. And you'll notice that negative sign out front. The idea there is that work done to the system becomes positive, work the system does becomes negative. So that just keeps our directionality correct. Now, using what we have so far, we're going to go ahead and apply Reynolds transport theorem. We'll use capital B as energy, and of course with Reynolds transport theorem we're looking at energy per unit mass that we're interested in. So here's our standard Reynolds transport theorem equation. We've got the system on the left, and we've got the control volume and control surface in those two terms on the right. Notice I've plugged in that lowercase e for energy, or our total energy per unit mass. So for energy in the system, I'm going to go ahead and substitute in the definitions that we wrote on the left-hand side of the screen. So you can see that I've got shaft work and pressure work, and in blue there I wrote density and then pressure divided by density. The reasoning why will become apparent to you as we move forward in the derivation, but having that additional density term in the denominator is going to become handy. And the right-hand side doesn't change, so I've just drawn an arrow here. So we can reorganize this equation, and I'm going to group together those control surface integral terms. So you can see now I've got just one integration over the control surface, and that's got both the energy and the pressure per density terminology. After that, we're going to make a few assumptions. We'll assume that we're working with steady flow. We'll assume that all of our velocities are representing average velocities perpendicular to the control surface. And by doing that, we both get rid of the dot product, and we can turn those integrations into simply keeping track of the fluxes into and fluxes out of our control volume. That time rate of change of control volume, the first term, of course, that becomes 0 because of the steady flow assumption. So now we've got an equation that looks something like this, where we're simplifying the left-hand side. And I'll write that equation again so that we've got it as a starting point for the second panel of this derivation. Rather than the summation of ins and outs, if we could assume that our system could be described by a single inlet and outlet, and if we substitute in the definition of energy that we had, so the small u with the hat over it, the velocities and the elevations, or the internal kinetic and potential, and then notice those pressure terms carry over from earlier in the derivation. We end up here, and what I'll do in red is divide both sides by mass, and then I'm going to simply go through and reorganize this equation. And at this moment, the energy equation should be starting to look familiar to you. We're not quite in the pressure form or the head form, so we'll do a few more things to reorganize this. If I go through and divide every term by gravity, and you can see that what I've done is I've changed the denominator of those pressure terms to specific weight, and a lot of those leading gravities on the pump and elevation and turbine terms disappear. And we'll take this last term where we've got those internal energies as well as any change in heat, and we're going to group that all together for the remainder of our work into a singular term called head loss. And so that's representing the net loss of energy due to changes in either internal energy or changes in heat that's generally extracted from the fluid. So friction we tend to think of as heating things up. That's the way that energy leaves the system itself. And so with that, we can reorganize to the final equation that you see here, boxed in red. This is the energy equation. This is not exactly the order that your textbook writes it in. This is my preferred order. I prefer it this way because it's sort of like telling a story of your fluid. So on the left-hand side, pressure, elevation, and velocity heads at the end point equal to pressure, elevation, and velocity heads where you began, plus the pump, which puts energy in, minus a turbine, which takes energy out, minus losses, which takes energy out. This is my preference because it helps me to remember which way the terms have to go in terms of plus and minus for pumps, turbines, and losses. One final aside on these pump and turbine terms. Sometimes you're given a work rate and you're interested in a head, or sometimes you will solve for a head and want to convert that into a work rate. You can do that here, where a work rate is equal to specific weight times discharge times the head itself. So I've noted that in purple for you, and of course your textbook goes both through those as well as how efficiencies work in these systems. Thanks for sticking with me for a little less than 10 minutes here. Hopefully that helps you see where the energy equation comes from. And I think it's important to note that although this comes from a very different derivation, this puts us nearly at the same place as Bernoulli, where we applied F equals ma along a streamline. So two totally different approaches, consistent with each other in how we can apply them to study moving fluids. Thanks everybody, and I'll see you in class.